So good afternoon, guys. My name is Anuj. I am an undergraduate mechanical engineering major at the University of Washington, and I'm ready to present to you my project on modeling fluid flows of heat exchangers with PINNs, or physics-informed neural networks. And I'll be discussing in depth more how we can leverage machine learning to accelerate the design process of heat exchangers while maintaining physical accuracy, which has become a critical challenge in engineering applications. So let's get started. So, understanding the problem. First, computational expense in both compute time and time in general. Traditional computational fluid dynamics, or CFD, models are incredibly accurate but computationally intensive, with a single simulation can take hours or even days to complete, and even longer time to mesh. If you've ever meshed TPMS lattices, you know what I'm talking about. But when you're iterating through multiple design configurations, this leads to extremely long design cycles that can stretch projects for weeks or months. So this brings in the need for surrogate models or machine learning architectures. This computational bottleneck has created a pressing need for these machine learning models that can act as surrogates, which are essentially fast approximations that can predict fluid behavior in the case of the heat exchanger without running the full CFD simulation and taking that time sink. So going into the hackathon problem in depth, we were essentially given a data set of 128 entries, which were for a heat exchanger, a tube and shell heat exchanger, which was filled with lattices, TPMS lattices, as you can see in this diagram over here, which actually has my optimal solution for the problem. So we were given 128 data sets of 3 inputs, which were the TPMS lattice size in this cell X direction, so the length in the X direction, the length in the Y and Z direction, which is one variable. So that's 2. And then the third one was the inlet velocity. And we were asked to train a surrogate model or machine learning model to predict the 4 outputs, which were pressure drop, surface area, mass, and average velocity. Now, and the second part of the problem was to write an optimization algorithm, which was intended to ensure that which was the right combination of your inputs to get the maximum surface area, which would lead to the most amount of heat transfer in regular thermodynamics for the heat exchanger. So that was the optimization part of the machine learning model, which would take your model's prediction and generate the optimal design for that heat exchanger. Now, breaking down the problem, we had a relatively sparse data, as I said, only 128 data entries, which is really little for machine learning models, which was a challenge for us to kind of train our model with such a sparse amount of data. But the model also required us not to extrapolate as much. We didn't have to extrapolate out of the data set as much. We didn't have to predict outside of the input data, which was pretty good for machine learning models, as traditionally machine learning models are not very good at extrapolating outside of that data set. So I'm going to introduce my approach to this problem, which was with PINNs, physics-informed neural networks. So I'm going to introduce the PINN right here. So like I was talking about, traditional machine learning limitations. So your vanilla machine learning model, your standard neural networks, they have significant weaknesses when applied to engineering problems. They lack the ability to extrapolate, like I was saying, well beyond their training data, and they perform poorly when data is sparse, which is the most important thing. You want your model to be able to predict, especially for this problem, since the data is sparse, we want to be able to be having accurate predictions within those spaces in the data. So traditional machine learning models are not very good at that because they're purely data driven and don't understand the underlying physics. So introducing the PINN, or the physics-informed neural networks, which was introduced in this paper in 2019 by Maserati, Paris Brokadakaris, and George Karniadakis, represented a paradigm shift. So instead of relying solely on data, PINNs incorporate physical laws described by partial differential equations, or PDEs, or even algebraic equations directly into their loss function. So in general, that loss function is the key insight. Traditional neural networks minimize prediction error against known data points, while PINNs go further. They also minimize violations of physics laws, what we call co-location points or synthetic data points. These are synthetic data points throughout the domain where we enforce those physics constraints, whether they be in the PDE, whether they be in an algebraic equation, even if we don't have the actual measurement data there, right? So that those co-location points, which we'll go in later in the go into deeper later in the other slides, is really what makes PINN special, as they are evaluated in the loss function in combined to the mean square error of the data loss, which is really important. So this approach allows the model to represent fundamental physics principles while still learning from available data, making it incredibly powerful for sparse data scenarios common in engineering, like for this heat exchanger in this example problem. So I think to fully demonstrate the PINN, I think it's important we can take a very basic example to see how a PINN works very effective with this kind of toy example of Newton's cooling, which is originally from an article on PINNs in a Medium article, which I will link in the description below. So essentially, this is the Newton's cooling law that states the rate of heat loss is proportional to the temperature difference between the object and surroundings. So mathematically, this is referred to as dt over dt equals negative k temperature minus temperature ambient, with k being the cooling rate. So the traditional approach to this would be a standard neural network would need extensive temperature measurements over time to learn this relationship purely from data. Meanwhile, our PINN can enforce the physical relationship at collocation points throughout the domain. So, and you can see at this in this image over here, I fed the vanilla neural network 3 data points over here for this pretty simple PDE, and you can see this is a standard neural network with ReLU activation. You can see it's already pretty inaccurate, and sure, it would be very, like, you can say 3 data points is not a lot for this neural network, but the best we can do is it will be accurate up to the 3rd data point, but once it's extrapolating past that 3rd data point where it needs to extrapolate, it really gets confused because it has no basis after the data is gone for the loss function, if that makes sense. So I'll go over to the collocation point over here. Now this is with the PINN. So even with the sparse temperature data points and temperature measurements, the model learns to respect the physics based off these, because we've added 250 synthetic collocation points to this graph right here, to this model. That way, at each of these points of the input domain, so on the x-axis, the model is able to evaluate if that point on the y would obey the governing physics, which is defined by this partial differential equation we saw in the last slide. So at each of these collocation points, it's able to evaluate that underlying physics, and we're able to see that the PINN is able to generate a much better understanding of the graph, and even predict what the k value, the rate of cooling, is off of that collocation points, which is pretty cool. So yeah, this is how essentially a PINN works with collocation points in a very simple toy example. So jumping back to our heat exchanger example for this hackathon, we were tasked to design map 3 inputs to 4 outputs, which is with no really governing PDE linking all 3 to 4 inputs to outputs. So it was a much more complicated system, but this toy example really shows how the PINN essentially works. And I'm going to just show you a quick, you'll have to excuse my pop culture reference over here to what I thought was the perfect PINN for heat exchanger, where we were given this challenge over here. So these are all the elements I'm using in the PINN. So I'll jump right into it. So the first part of our PINN is our straight up MLP design. And I like to talk about it. It is a 2-stage with 10H activation and batch norm on it. I have about 16 neurons on each layer, so it's a pretty shallow network. And your first question might be wondering, why not go deeper? So while these deeper networks can capture more complex relationships, which may be needed for this, they also introduce a huge amount of training challenges, which I learned the hard way, actually. And especially with the mixed loss functions we use in the PINNs, shallower networks often provide the right balance of expressivity and trainability for these applications. We also experience a lot of overfitting in a deeper network, so that is kind of why that drove the design decision to go to a more shallower network. And then the question you may ask is the why 10H activation. So we use the 10H activation rather than the more common ReLU or leaky ReLU function, because 10H is differentiable everywhere and has bounded outputs, which is essential when we're computing derivatives for physics constraints. So this smoothness really helped with the gradient flow and the numerical stability. Um, 10 Rayleigh and leaky Rayleigh often, because of their non-linearity functions, often resulted, or lack of non-linearity functions, especially for a complex relationship like this heat exchanger, often led to more exploding gradients and disappearing gradients, and especially in a shallow network, that is very bad because we only have the weight of each neuron really increases because there's not as many neurons in that network, right? Um, and then the third question for this MLP design was the batch norm, which is perhaps one of my biggest shortcomings with the previous MLP design was not to have batch norm. Batch norm helped a lot, and the reason why it helped a lot was actually because of the scale of the physics loss, and normalization for the data in particular. The scale of the physics loss, for example, of the pressure drop, which was in pascals and was in the 8,000s, right? And then the mass was in the hundreds. So the scale needed to be normalized, and we did that with the standard deviation being 0, and then the mean being 1. So yeah, that's kind of what drove the MLP design. And I'll go into these two diagrams right here, the MLP architecture visualization, with the batch norm and 10H activation, and the MLP map as well. So I'll go into two main other architecture driving decisions that we made was the initialization function. And it's important to note that since we were using 10H activation, not Rayleigh or not leaky Rayleigh, it became incredibly important to pick a correct initialization function due to the fact that 10H in particular was very sensitive to these initial weights. So that is why we chose the Xavier initialization over here, which has the probabilistic distribution of both fan in and fan out for input and output, which is very good. So it maintains that stable gradient flow throughout the network, which is critical when you're dealing with small data sets, deeper MLPs, and 10H activations. So the Xavier initialization really prevented the vanishing or exploding gradient problem that can plague our physics-informed models. Like I said before, we tried it with the LeCun initialization, and we found that Xavier is preferable because it enables that fast, reliable training and prevents some neurons from becoming dead or saturated, which is a big problem in case of a shallow network. So this is the formula that defines Xavier initialization, and the most important part is that it factors fan in and fan out, where LeCun does not factor and out. It actually just only factors and in. It's optimized for inputs only. Secondly is the atom optimizer. So for optimization, we use the atom optimizer. Pretty standard. With pretty standard option instead of the SGD. Atom automatically or stochastic gradient descent. Atom automatically adapts learning rates, eliminating the need for the manual tuning, which is a huge advantage when dealing with the complex mixed scale loss functions we have in the PINNs. The data loss and physics loss components often operate at different scales, and Atom handles this mixed scale. The noisy loss landscape makes it much better than the classic stochastic gradient descent. So this ensures that consistent convergence we need to have predictions spot on for our PINN. And it's important to note that both the MLP design and the Xavier initialization and Atom optimizer were both critical design decisions that really laid the foundation to making our PINN successful, and we're very trial driven, as in we tried different initialization, different optimizers, to see what would really make the best fit. So into the secret sauce of our PINN, which is the loss function. Up here you can see the general formula for loss, which is loss total equals for the PINN, obviously, which is the loss of data loss, which is calculated with the mean square error, which is over here, plus the physics loss, also mean square error at the co-location points, is what makes your total loss. Yeah, so the physics loss was really split up into three main physics relationships, which we developed and kind of executed in our loss function to kind of shape. As I said before, there's not really a PDE that defines the three outputs to the four, or three inputs to the four outputs. So it's not like our toy example with the Newton's cooling. We kind of had to find general relationships that were able to show the PDE, or show some relationships between one input and one output, or things like that that really shaped our loss function. So going into it, I'll go into it physics relationship 1. When studying the data, I found a quite a good linear relationship. This is a simple linear regression plot between the velocity inlet, which was an input, to the average velocity. It was almost perfectly linear, almost I think 0.01 off. So I was able to drop that simple formula of V inlet equals 4.98 V average. So this ties one input to one output in a linear way, which was really helpful. So they weighted this very heavily. So that's our simple physics relationship 1. Physics relationship 2 was by far the one that took the most time, which is a modified Darcy-Weisbach equation for fluid flow through tubes. Now it's important to know that the Darcy-Weisbach equation here, listed in the bottom left, does not really apply directly to the heat exchanger over here, because the friction coefficient changes with the lattice size, so it's difficult to model this. But with understanding that L over D, which is length of tube over hydraulic diameter, really is a geometric term, I'm able to shrink down this equation to delta P equals friction coefficient times V squared over 2 times geometric term, right? And the relationship I really want to drive in my model is saying pressure drop equals V squared over 2 times the geometric term, which is X cell times YZ cell for the TPMS lattice. Obviously, I'm keeping the fanning friction coefficient a little bit constant here, but I want to drive this relationship home a little bit in the model. And it's important to me that I don't weight this as high, because the data obviously has its own friction coefficient, has its own L. However, if I can enforce the relationship where V squared, or the velocity average scales proportionately squares quadratically to the pressure drop, I'm able to give the model a little bit support in these co-location points, where it can kind of try and get that relationship, at least see the relationship in the co-location data. So our physics relationship 3 is pretty simple actually. It's just making sure that we add penalties for negative predictions. For obviously pressure drop can't be negative, mass can't be negative, surface area can't be negative. And to make sure that all of our outputs remain physically realistic and plausible, which is pretty important for extrapolation. Real quick, I'll go over the training loop and data validation and basically results over here. So we had 1,000 synthetic samples uniformly covering input space for the physics regularization. We used the combined loss used for backpropagation and weight updates. And I found gradient clipping quite helpful in the case of exploding gradients due to scale issues still happening. So that really helped with the training loop as well. Over here, you can see our normalized RMSE errors. The mass was the best because of through the data, we could see it relates very heavily to the geometric coefficient. So it had nothing to do with the velocity inlet. Surface area was also a geometric term, so it also mapped pretty well. Our delta P had a 10.8, which was the worst, which we were having trouble, and I'll keep working to improve it on the delta P pressure drop. It didn't converge as good for the delta P as it did for the mass and surface area, and average velocity was also reliant on velocity inlet, so a little bit error off was there. So I'll go on to the inverse design. and optimizer. So for this one, we employed more of a heuristic optimization strategy rather than a Bayesian optimization. I did implement a Bayesian optimizer, but I found that the heuristic actually was better. So I'll explain the heuristic real quick. So it starts with, it's basically a three-pronged approach where we do the grid search, which is systematically exploring the parameter space by evaluating the PINN predictions on a structured grid of input combinations. So the grid search really makes sure that we are not leaving any part of the parameter space unexplored, while the random search implements that random sampling to explore the parameter space more efficiently with more data points, which covers more regions that the grid and the grid search might miss. And then both methods track the best feasible design that maximizes surface area while satisfying engineering constraints like pressure drop limits and manufacturing constraints. Um, and then lastly is the local refinements. So once we identify the promising regions, we perform fine local perturbations around the best found parameters, which involves making small random adjustments with bounds and rechecking feasibility. And one of the cool things I think I did was, or I guess not cool, but more simple, was with the errors. With the errors I made, or in the trying to make this optimization get closer and closer to the optimized result, I was able to put that data back into the model, so it's able to generate better predictions because it has 10 extra data points around the neighborhood of the optimized surface area, optimized inputs for the max surface area. So in the end, the model spit out 15.211 as the X cell size, 25 as the YZ cell size, and 252920.92 as the inlet velocity. And when you plug this into the NTOP computer CFD model, you get a max surface area of 23,490.72401. Mass just underneath the threshold of 125, delta P well underneath the threshold of 8,000, and average pressure just above the threshold of 520. So every design constraint is, our manufacturing constraint is filled out. So this optimizer was successful. For context, the winning hackathon submission, which got first place, I believe had a surface area of 23,670 around. So I wasn't too far off, and certainly proud of that effort over there. And it's important to see how these pins can be applied throughout future or broader applications. Pins can accelerate the discovery of new materials by incorporating physics laws governing material properties. I know Rolls-Royce is doing research on pins for material properties for jet airplanes. It can be used for thermal, fluid dynamics, like we just saw, aerospace, and I even think the biomedicals field is doing biofluid mechanics, medical device design that all involve physical constraints problems with sparse data. So a lot of things over here. And this was my first project with machine learning in mechanical engineering, combining those two fields, which I think we'll see more of in the future. I was quite happy with my results, since this was my first time really doing machine learning and programming as well. I think it was quite interesting. I got pretty close to where the ideal optimization, like I was saying, is pretty close to what the winning result was. So I was definitely proud about that. In the future, I definitely want to see if I'm able to do something, maybe another problem, but use a different architecture like gradient boosting decision trees. I think that was the one the winning team used. So we will see if we can use that in the future. But definitely a good starting point for this project portfolio I'm building, and I hope you stay tuned if you learn something. Hope you drop a like and let me know if any other projects I should work on. Thank you guys so much for watching.